Hi everyone, I'm Philip Newman, and this is not a gas walkthrough, as you probably figured out from the title and the thumbnail. This is a Sudoku theory video, and I'm going to be talking about nerd snipes. If you don't know what a nerd snipe is, this comes from an XKCD comic, and the idea is that a nerd snipe is a really interesting, theoretical, usually, problem that is so distracting to the target of the nerd snipe that they might, say, get run over by a bus because they're thinking about the problem. I don't think I'm going to get run over by a bus. I am upstairs in my office. So it would take a really unlikely set of circumstances for me to get run over by a bus. But I am known for getting nerd sniped quite a lot on the CTC community Discord. Somebody will pose an interesting problem about Sudoku or about puzzles in general, and I will get absorbed in them for hours. So I'm going to talk about some of my favorite nerd snipes that I have participated in. Eventually I might cover some that somebody else set or thought about or found or was involved in the theory crafting. But I'm going to start with the ones that are most relevant to me. One of them is today's gas, which is the minimum number of thermos that you need for a unique Sudoku. I'm not going to touch on thermo in this video. I'm going to start from sort of the beginning, which is classic Sudoku. So a lot of you may know that you need at least 17 givens to have a unique solution in classic Sudoku. And if you didn't, that's what this paper is telling you. There is no 16 given Sudoku. How do we know that, though? Naively, you might think, well, maybe we've looked at every possible solution grid in Sudoku and picked 16 givens in every possible way from that solution grid, and then we checked if it's unique. And once we ran through all those possibilities, we found that there weren't any that were unique. The problem with that is there is a large number of possible solution grids. It is 6.67 times 10 to the 21st power. And there's a large number of ways to choose 16 from a set of 81, which is the number of cells that we have. If you combine those two numbers, you end up with something on the order of 2 times 10 to the 38th power, which is just a huge number. Never mind that you then have to check for uniqueness for each one of those. So we don't want to do that. We can simplify this some, though. So let's start with the solution grids. And I'm going to bring up a puzzle as an example. This is a 17 given classic. It does have a unique solution. But I want to talk about symmetry groups first. There is a large number of possible solution grids in Sudoku. However, some of them are effectively the same. And just as an immediate example, there's an 8 in this grid. I'm going to color it orange. If I change that 8 to a 9, would this still have a unique solution? The answer is yes. All I would have done is swapped all of the 9s and the 8s in the solution grid. Changing that 8 to a 9 doesn't change the core characteristics of the Sudoku. It's a different puzzle. It has a different number in that cell. But they solve exactly the same, just with 8 and 9 swapped, right? So that's one symmetry. You can always take any 2 digits and swap them. And you end up with a different puzzle, but the same puzzle. So there's a term that we use, essentially different. So essentially different puzzles are puzzles or solution grids that cannot be swapped by this sort of symmetry operation. There are a few more symmetry operations. You can rotate the grid. If I rotate this grid 90 degrees, I haven't really changed anything about the grid. It solves the same way, just in different cells. So if this has a unique solution, then the rotation will also have a unique solution. If this doesn't have a unique solution, the rotation also won't have a unique solution. It doesn't change anything. You can also swap rows as long as they're in the same band, or columns as long as they're in the same stack. Swapping these two rows, the only effect it would have is anytime I make a deduction in row 1, instead I'm going to be making that same deduction in row 2. You can swap entire stacks and swap these 3 boxes with these 3 boxes. So these are the types of symmetry operations. Reflection is the other one that I didn't mention. These are the types of symmetry operations that you can have. And that reduces our number of possible solution grids down to a more manageable 5.4 billion. That's still a big number, but it's a lot more manageable. Now, the problem is, even reducing that number, we still have the problem of choosing 16 givens out of 81 cells. And that is what this paper is about. This is about overcoming that problem so that we don't have to check every possible way to choose 16 givens. We can just check some of those. The way that they do that is by looking at what are called unavoidable sets. So this is just a random solution grid. I had Ranks Solver and FPuzzles generate a random solution, copied it over to Sudoku Pad, and I'm just going to talk about what unavoidable sets are. So there's an example right at the top here, and you might recognize this sort of thing. You might have seen this as a deadly pattern. If I end up with something like this in my solve, and I don't have any other clues, I have a problem. So there is no way to resolve this logically. I could put a 7 here and a 5 here, like that. That is a solution. But I could also swap those digits, and that is a solution. The problem is that these 4 cells don't interact with anything else if they aren't filled. Changing the 5 and 7 around in these 4 cells doesn't affect the rest of the grid. So this is an example of what is called an unavoidable set. I'm going to highlight those in orange. What an unavoidable set is in a solution grid is a set of, could be 4 cells, it could be 6 cells, it could be 8 or 9 cells, could be larger, but it's a set of cells such that if I didn't have any givens in those cells, if I didn't provide any of these digits, then I would have more than one solution. I would not be able to resolve the Sudoku. So in order to have a puzzle from this solution grid, I have to provide at least one of these as a given. I could provide this 7, I could provide this 5, something to resolve these 4 cells. Now that's just one example. There are a lot of examples of deadly patterns or unavoidable sets in the solution grid. And so we can look for some more of them. This one is kind of neat. This is a 6-cell pattern that spans 3 boxes, and it kind of turns the corner here. You can also have them on multiple digits, rather multiple. You can have them on 3 or more digits rather than just 2. So this is an example of one that is on 3 different digits. And it might not be immediately obvious, but if I remove all of these, I could put the 1 here instead. And now this is going to become a 2 and a 1, and this is going to become an 8 and a 2. And that is also a valid solution. So if I don't give any of the digits in the green cells, I get more than one solution. There's another one here. I'll just highlight one more. So for each of these colored sets, I need a given in them. I need a given digit in orange. I need a given digit in blue. I need a given digit in purple. I need a given digit in green. Now, there are a lot of these. We could keep searching for them. But I'm going to have to satisfy all of them. So in this particular example, this single cell is covering 3 different sets. If I put a 2 in this cell, I don't have to worry about this purple pattern anymore, and I don't have to worry about the blue pattern, and I don't have to worry about the green pattern. So what the paper is doing is generating a bunch of these unavoidable sets. I believe they're finding all of the unavoidable sets up to a certain size. I want to say it's 12 cells. That may be wrong. I'm not going to scroll through the paper right now to find out. But they generated a bunch of unavoidable sets. And then they looked at what's called the hitting set. So they looked for all possible ways to assign 16 given digits such that all of the unavoidable sets are covered. And that is a much smaller group than just picking 16 random givens. If all the unavoidable sets are covered, then they can check whether it's unique or not. If they're not covered, then they already know it's not unique, so they don't have to check that possibility. They can just skip it. So this is reducing the problem of picking 16 givens down to picking 16 givens that cover all of our unavoidable sets. So that's how this worked. I did want to mention down here the statement, due to the sheer number of Sudoku solution grids, a brute force search would have been infeasible, but we found a better approach to make this project possible. And that's what we were just talking about. The original version of this, their original program called Checker, would have taken over 300,000 processor years in order to search all the Sudoku grids. Fortunately, they updated the algorithm and got that down to 800 processor years. So this program ran for 800 processor years, and I believe the actual search took about 1 actual year, because it was run on multiple computers, multiple processors. And that's how they proved that there are no 16 clue puzzles. There are quite a few that get close. There are 16 clue puzzles that only have 2 solutions, but there are none with a unique solution. As a follow-up to this, and I'm going to come back to this grid, this is actually a important grid in the history of Sudoku. I've titled this 49,158, and it is by Blue. Blue is a user of a Sudoku forum where the search for all of the 17 given Sudoku puzzles was kind of an ongoing thing. And I was actually part of a computer search to verify that this is all of them. There are exactly 49,158 17 given puzzles. Now, obviously, you can switch this to a 9. That's not counted as a different puzzle. But 49,158 essentially different Sudoku puzzles with 17 givens. And the search for that took a similar form to the search to prove that there is no 16. It took longer because there are more ways to place 17 givens than 16 givens to hit all those unavoidable sets. Took many, many years and a lot of computer power, but it was finally done. So that is one of the nerd snipes. We've spent a lot of time thinking about this problem. I say we, mostly other people, for this particular problem, but also a lot of computing power to prove this. There is no elegant logical proof that you need 17. This is an example of a proof that requires a computer search. Maybe someday somebody will find an elegant proof that you need 17. That would be very cool. But there are a number of famous problems in mathematics, like the map coloring problem, where the proof relies in some part on computer search. We narrow down the possibilities as best we can, and then we rely on a computer to check for us to make sure that none of those possibilities work, or all of those possibilities work, or whatever the problem is. Okay. So that is classic Sudoku. Now we know that you need at least 17 givens. So next, I'm going to look at Killer Sudoku. And this is probably the one I am most famous for. And I'm going to be looking at how few cells you need for a unique Killer Sudoku. So just naively, I'm going to use cosmetics here. Just naively, how few? What's our lower bound? Well, let's say that this had a unique solution, whatever it was. How many cells have I got? This has 16 cells. Could this have a unique solution if I gave the totals? The answer is no. And the reason we know the answer is no is knowing the totals of these cages doesn't provide more information than just telling you what is in those cells. So if I only have 16 cells in my grid that are in cages, I can't have a unique solution if that's the only information that I provide. So we know we need at least 17 caged cells. How low can we go? Well, sort of a naive approach would be something like this. And I'm going to do this in kind of a weird order. It will make sense why I'm doing it in this order. But let's say we allowed 1 cell cages, just to start with, for the sake of argument. Let's say we made this a 1. We're going to come back and get rid of this. Now, let's say we looked at this and also made it minimal. The lowest we can put in 2 cells is 3. We can have a 1 and a 2. But because we already have the 1 here, that's resolved. The 1 has to go in column 2, and now the 2 is in column 1. What's the minimum in 3 cells? Well, we could have a 6. And that's forced. What's the minimum in 4 cells? 4 plus 3 plus 2 plus 1 is 10. All right, what about 5 cells? 15. What about 6 cells? That could be 21. What about 7 cells? Well, that would be 28. And you see where this is going. We've got some green digits here. That means we're almost unique. What about 8 cells? The minimum is 36. And now we have a unique solution. So this is kind of cascaded down. We have a 1 cell cage, which forces the 2 cell cage, which forces the 3 cell cage, and so on. And we could even have a 9 cell cage here. We could have a 9 cell cage anywhere. It sums to 45. Now, this isn't legal for a minimum killer because we have this 1 cell cage. But we can fix that. We could make this an 8 cell cage instead, just missing the 1. And so this might kind of be a naive first attempt. Can we do better? Well, instead of the 7 cell cage, we could have the 2 cell cage. Instead of this 5 cell cage, we could have a 4 cell cage. Instead of the 6, we could have a 3. So this is still unique. And this puzzle now has 34 cage cells. This was kind of the first attempt at this that I saw. It was thought for a long time that this was the best you could do in terms of number of cages. This only has 8 cages. And I call this kind of the trivial approach. It's trivial in the sense that all of the rows are in the same order. Just 9 to 1 descending, just starting in different places. So 9, 8, 7, 6, 5, wrapping her back around 4, 3, 2, 1. Now, can we do better than this? just with an approach like this. And this is the reason that I kind of put these in a weird order. If both of these were 1-cell cages, we would only have 20 cage cells. That's pretty good. 20. It's not too far from 17. Well, it turns out, and I only discovered this a little over a year ago, that just from this grid, if we add that cell and give the totals from that particular solution grid, it's unique. And it no longer has any 1-cell cages. So this is 22 cells. I actually posted this 1 year ago today, and posted a little explanation about where this came from. This is kind of the video version of that. So, 22 cells. Is that the best we can do? Well, no. And even 22 cells a couple of years ago would have seemed really low, like really unlikely. It's a little silly in retrospect because of how simple this was to find. But we can do even better. And we can go all the way down to 18 cells. Just one away from 17. I spent probably 25, 30 hours on this over the course of a week. Starting from a pretty high number of cage cells. I think my initial effort had 32, and I just kept reducing it down all the way to 18. This is the minimum for killer, with no other rules. We know it's the minimum because while our lower bound was 17, we now know all of the puzzles that have 17 givens. And so there's a way to check whether any of those can be turned into a killer Sudoku by replacing all the givens with cages. Now, obviously in this case, we can't just put a 1-cell 8 cage here. So we have to do some things first. We have to rearrange rows and columns so that all the givens have neighbors. We also have to check for cases like this. So say this was one of our potential cages, and we made this a 9 cage. Well, one thing we have to check is, what if these two digits were swapped? What if this was a 5 and this was a 4? If that has solutions, then there's no way that the killer is ever going to be unique, because we can always swap digits in a killer cage. So that's another thing that we had to check. And ultimately, we searched through all 49,158 possible 17 given Sudokus to check if any of them even met kind of these filters. Only one of them did, and that one can't be made unique with just killer cages. It's just not possible to disambiguate all of the low digits and all of the high digits. Best you could do is 1,000 and something solutions. I don't remember exactly. So as soon as we determined that there are no more 17 given Sudoku, we knew that there is no 17 caged cell killer Sudoku. So 18 is the best you can do. This was the first one that I found. There are probably 8 or 9 known now, including some that only have 2 cell cages, which is kind of neat. But hopefully you found that interesting. I'm going to provide a link to this puzzle. This is not gas. This is a tricky puzzle. A 3-star difficulty, something like that. Simon solved this on Cracking the Cryptic. Took about 25 minutes, the video. And I set this entirely just trying different things. plugging them into a solver like this, and well, this can be 11. Hey, that's unique. Can this be 12? No, that's not unique. And so on, until I found that one that was unique. It happened that the solve path for it is absolutely gorgeous, especially the opening. So check it out if you want a little something harder. And I'm hoping to do some more videos on nerd snipes, some of my favorite nerd snipes. I have a tendency to ramble, so let me know what you're interested in, and any specific questions you have about these types of puzzles. Next time I'm going to talk a little more about killer, because there are some more questions we can ask, like how few cages can you have? The answer is not 8. You can actually get down below 8. So I'll talk about that and maybe another variant. But hope you enjoyed this. Let me know. Comment, like it if you liked it. Subscribe if you haven't. All that sort of good YouTube stuff that the algorithm loves. And I will see you next time.